Okay, so we've talked a lot about moments about a point, but what about if we want to have figure out how a force would cause a moment about a particular axis? So a fine example here, a hinge. It's not just a single point we're rotating around. It's a series of points. It's a series of points that are in a line. Different forces, obviously based upon their location and orientation, will cause one end of the hinge there to have a different response compared to another. So we can calculate how that works. So that involves using the dot product of two vectors, also known as the scalar product. In this essence, the definition of the dot product is a quantity. Again, the result of the dot product is not a vector itself. So it's a scalar result. It gives us a magnitude. It doesn't give us a particular direction, and we'll come into why we want to use that later. But essentially, the dot product of two vectors is basically the two vectors multiplied, the magnitude of the two vectors multiplied by the cosine of the angle between them. So essentially, if you have two vectors that are parallel with one another, parallel and in the same direction, then you are going to end up with a dot product that is just equal to the magnitude of those two things together. So again, they unlike the cross product, they are commutative. The order doesn't matter. They don't. There's no because we're not ending up like we did with the cross product with the final result being a vector in a particular direction. They're still distributive. They're not associative. Essentially, you can't go and take the dot product of these two. Can't take the dot product of something and then take the result of that and take the dot product of take the result of that and then take the dot product of it and something else. Because once you take the dot product of, say, this P and Q here, what you end up with is a scalar. So then you'd have a non-vector quantity that you're trying to take the dot product of, and that just doesn't work. It's not a vector, so you can't take the dot product of it with another vector. So when we're going to Cartesian coordinate systems, essentially you break it up by saying that the dot product of the two vectors is the x components of the x components of both vectors multiplied by one another, plus the y components of each vector multiplied by one another, plus the z components of each vector multiplied by one another. So, like I said, essentially, if we're working with just vectors that are unit vectors, any of the unit vectors, the dot product of the unit vector with itself is 1. The dot product of a unit vector with a different unit vector is going to be 0. So because I and j and k and I, those are all perpendicular to one another. So you take those magnitudes multiplied by the cosine of 90 degrees, you get 0. So essentially what this allows us to do is it allows us to project a vector onto a given axis. So the projection here the projection of this vector p here onto this line that is from O to L is based the magnitude of that can be found using a dot product. So basically it'll be based upon the angle and between the two vectors in question. So again, obviously the projection of a vector onto an axis that it's parallel with is going to be just the magnitude of that is just going to be the magnitude of the original vector. Whereas again, if we take a different vector here that is perpendicular to this line OL, then projecting that onto this vector would just give us 0. Similarly, we can simplify things if we already know what the unit vector of the axis is. So that basically just means that we take the dot product of the vector and the unit vector in question, and then essentially it's broken up into the the x, y, and z components already. So the point here is basically that this is what allows us to figure out how a moment applied at a particular point, how a moment that is caused by a force applied at a particular point will cause a rotation about an arbitrary axis. So we already know how to calculate the moment about a particular point. We take our displacement vector here, take the cross product of the force, and that gives us our moment about O here, about the axis. We're not necessarily concerned about the moment about this point. We might be worried about the moment about an axis that passes through that point. So what we do is we basically we can calculate that moment and then project it on to this axis here. So we got this unit vector here that defines the axis that we're worried about it rotating around. We take this vector here and project it upon this axis here. Now you notice that the resultant, the result, the MOL here, isn't listed on this graph here because again it isn't a vector itself. It can't really be shown on the graph. It's just a magnitude. But the magnitude of that of the dot products of those two vectors basically gives us the tendency for this force applied at this point to cause rotation about this axis. So we can also do something similar for to calculate the moment of a force about an arbitrary axis, one that doesn't necessarily pass through the origin. So similar idea. Basically, we just need to do what we discussed previously in order to figure out what the moment that this force here causes about a point on the line. You could pick B, you could pick C, you could pick any point upon the line, and then take the dot product of that resultant vector with the unit vector of the of the axis in question, and that'll give you the tendency for the moment to the tendency for the force to cause rotation about that arbitrary axis, the magnitude of that. Now we'd like to point out again that that the result that we end up here is a scalar product. So again, we're not showing that as a vector on our graph here. So the next concept we'd like to discuss is a couple, the moment of a couple. Now we've got this old steam pipe valve here. Now looking at this, we apply force upward and we apply force downward and apply force upward on either side, and we're trying to crank it, versus if we're pulling to the left at the top and to the right at the bottom, again we're still cranking it with the same amount of force. Which one of these is going to cause the steam pipe to open faster? Which one is going to cause a larger moment in order to allow you to open that valve easier, or to overcome the resistance? Now I really hope that most of you are saying, well, it's the same. That is correct. So the concept of a couple is basically a pair of forces that are acting in equal and opposite directions, but separated by a distance. And those just now essentially when you do so when you apply those forces to a body, the actual forces cancel out, so you're not providing any tendency for lateral movement of the body in question. So it's still working out for the equilibrium there, but it is going to cause it to want to rotate. So that applies a force couple applies a pure moment to the body in question. So some things that we can tell you about the moment applied by a couple. Essentially, different moments that are applied to an object can be considered equivalent if a few things match. The first off is that the combination of the magnitude of their forces multiplied by the distance between them, if those two quantities are the same for different moments, then they're causing the same tendency to rotate. So if I've got my pen here and I'm applying a smaller force on the outside tips of the pen, then it's going to cause the same amount of rotation as if I was applying a larger force on the closer to the center. In order to have equivalent moments, so they do need to be in parallel planes. Parallel planes, not necessarily the same plane, but as a parallel plane ensures that when you essentially calculate the orientation of the moment that's generated, that it has the same unit vector. So the moment that you're causing needs to be oriented the same way, and they need not just the line of action. They do need to have the same sense. They need to be acting in the same direction. So for these two, these would be considered equivalent moments here, as long as those things, as long as those conditions are met. You'll note that these are both going to be causing counterclockwise rotation. That's going to be what we call a positive moment. So you can apply a moment at any point on the object, and it's going to have the same effect with regards to equilibrium conditions. So if I'm, if I have this calculator here, and I'm applying a moment here, or applying a moment here, or applying a moment here, essentially, the stuff that you're going to have to do to the calculator, the forces that are going to need to be applied to the calculator by other external forces remain the same. Once, obviously, once you actually start twisting, then it changes kind of where you're twisting about, depending on where you apply the moment. But this is a statics course. We're not worried about what happens when it really starts twisting. What we're worried about is what happens when things aren't twisting. What sort of forces are generated when loads are applied to objects that aren't moving? What sort of stuff needs to happen in order to ensure that thing doesn't move at all? So those moments are free vectors. They have a directionality. They have a particular unit vector, but they can be applied at any point, and it's going to the effect on the object is going to be the same. Not too shockingly, yes. So the way we represent them still follows the right-hand rule. Got a moment couple here. We figure out the magnitude of that moment couple based upon the force times the distance between those parallel lines, and that gives us our moment here. It's oriented coming out of the page, out of that plane, based upon the right-hand rule. So you can consider that to be a single vector with a particular orientation, or you can break it down into its component vectors, and essentially it's the same thing. If you add a tendency to twist about the y-axis, a strong tendency to twist about the y-axis, with a little bit of a tendency to twist about the x-axis and the z-axis, that'll result in kind of the same tendency to, this particular combination of a tendency to twist about, a tendency to twist about this, about an axis oriented in this direction. So that allows you to, break your couples down into vectors, and then after that, it makes it easier to add and subtract the total moments that are being applied to an object. We also have this concept called a force couple system. So basically, this is what allows us to shift around the forces that are on our diagram and replace them with equivalent forces. So in this little diagram down at the bottom here, we've got a force that we're applying at point A. And if we take that object and also apply a force, an equal force at O here, an equal force at point O, and an equal and opposite force also at point O. Well, if you're applying forces that equal opposite at a single point, the effect that's going to have on equilibrium is zero. You're pushing and pulling at a single point, equal and oppositely. Then that doesn't affect the equilibrium of that object. So this force here and this force here, that forms a couple. So we can they've got equal magnitudes. They're acting in they've got they're acting kind of parallel to one another but opposite, and they're separated by a certain distance. So essentially what we can do is we can take this force, and replace it with a moment couple that is the same, and replace that with a moment couple, and this system here is going to be equivalent to this system here, which is going to be equivalent to this system here. So essentially, if we want to play around with the forces that are applied on a free body diagram, we can move around those forces in order to allow for us to simplify our diagram by using a force couple system. So essentially, so essentially, another way to look at this would possibly be, right now we have, if this force is applied at point A, and we're measuring from the origin here, then this, in this situation, this force measured from the origin is applying a moment to this object as well. So what we could do is we could just figure out how much that moment would be, which is the same amount as would be caused by the shift, and we can just move that force over to the origin, and then also add the same amount of also add add a moment that's applied to that body in order to represent the moment that was originally there. So that basically allows us to shift these things around and shift our forces perpendicular to their lines of action, keeping in mind that previously we already talked about the fact that we can shift our forces parallel to their line of action without changing the equilibrium condition. Now we can also change their line of action and figure out what sort of moment would be generated, and then just represent that on our free body diagram. Another possible way of looking at this would be to say that if we started with this force here and moved it over to O instead, that is essentially going to be if we actually did that change, then measured from A, that would cause that shift would cause a moment where one didn't previously exist. So we could nullify the effect of that shift by adding a different moment that counteracts the moment generated by shifting from A to O. So not too bad. The calculations are straightforward based upon what we already talked about. Figuring out the magnitude of that moment is just based upon taking the displacement vector from O to A, crossing it with F. Generally speaking, you're often going to know just the amount it was shifted, per se, the amount that the line of action of the forces was shifted, and so you're going to know that perpendicular distance instead of necessarily knowing the location of 2 points along the line here. Beyond that, we can go ahead and consider these systems to be equivalent, which again can be useful when we're trying to simplify the forces on our diagram and essentially figure out what the equilibrium conditions are. And that's about it for now.